Bismillahirrahmanirrahim. Assalamu alaikum. Uh,
Good afternoon, sir.
Good afternoon, Ashley. How are you?
Doing
Oh,
okay, sir. I hope you're doing well as well.
thank you. Thank you very much. It means everyone hears me properly. So, alaikum assalam, we just jump. So, we will be starting our today's module, and uh, you will be starting from the concept of machine learning, and we will be trying to have a project, sample project as well, uh, to do some trainings, actual trainings, how to combat conduct a machine learning problem. But still, before that, we have to understand the concepts of machine learning. So, machine learning is a field of computer science which enables computers to learn from data uh, and improve the performance of data based on specific tasks that you're giving to that um, uh, them. Uh, Without being explicitly programmed. It means previously, when before machine learning concepts, it was in a way that for each and every step that computer should think or should do something, you had to code. So I'm talking about 80s, 90s, and even the first decade of um, um, 2000 to 2010. It was in a way that for each step that computer to decide to do, you have to write a code for that, and then computer would just execute that specific code, and that specific task would be appeared uh, on the computers. So this was the way that the computers were programmed. But the concept of machine learning, which has been emerged in a way that now it gives the computers a type of semi-autonomous decision-making capacity. So this is how you code something, then you show the computer a pattern. Computer will follow the pattern and find the next task, the next solution, the next response to it. So this is why machine learning is very important. Machine learning is actually the basis of all AI, so artificial intelligence, these chatbots. Sorry, I just closed the windows. So this is how the artificial intelligence, the basis of all artificial intelligence and networks is machine learning. And it's very, very important that you have to understand that how computers predict the next activity, the next action. So to the level that you are producing a very well trained model, to that level, um, your model will predict accurately. For example, look at um, ChatGPT or Gemini from the Google. These are chatbots. These chatbots are producing the responses, but they don't know actually the exact responses. They don't know actually how the texts or the context behind the text are there. No, the point is that they are knowing is actually this is the mathematical calculation of the patterns. So they have a huge amount of data. They they embedded those data into their minds, to their computer minds, and whatever you're asking, so they're searching for the similarity next response from um, from those data. So this is how, for example, and they're programmed in that way, that to predict the response for your query. And you know that now that the competition is that whoever develops proper models to predict more accurately, that will be much more now earning money in the business and reputable AI chatbot. So this is how the basis of all these things is actually the machine learning. And this is how um, it involves type of algorithmic methods that identify patterns, then make decisions and generate predictions from data. So this is a very uh, um, brief understanding of machine learning process that you have to have data collection, then you have to pre-process the data, then you have to select the features from that data, then you have to split the data. Then you have to train the model. So why you have to split? You have to split the data into training and testing. Or why training and testing? On the training portion of the data, you will train the model. Computer will learn from that portion of the data. The um, from that portion of the data, the computer will understand the patterns and learn from that. And the testing portion, when the pattern is learned and the model is developed, then you have to test it back on the test side on a small amount of data, which is in the testing split. So you have to test the model that how much is the accuracy of that model, how much that model is actually accurate there. So this is why it's called splitting the data. Then you have to train the model and evaluate the model. Then you have to validate the model, and then model prediction, then performance evaluation. These are the steps within this model development, machine learning. You have categories of machine learning, and for machine learning, categorized in different aspects and types, but we will be just mainly focusing on supervised learning, unsupervised learning, and reinforcement learning. These are the three very common categories which are heard by everyone. And what is the supervised learning? Supervised learning is actually model that you have developed. It learns from label data, examples, classification, regression. So then you are coming to what's label data in non-label data, and so the model actually learns from that, and then predicts something for you. So do you remember we did a regression prediction for for one of the data sets? The data was already labeled. Yeah, if you remember the chunk data set, the guy will be chunk will the result of that decision. For example, last purchase. When was the last purchase? Yeah. So the customer will churn or not churn. Yeah. So these were two categories. So actually, we did the labeling of the data, and we provide already labeled data to the computer, and computer will understood the whole pattern there, and then for the unseen data, if you remember, we generate just totally a new data frame there. Then we give it to the model and ask the model, okay, now, okay, just predict it, and it did prediction, and the prediction was not good, but still, um, that was the process that we have conducted, because we give the model, the computer, labeled data. It means we give the computer data, which we said, yeah, that is that is right, that's wrong, that's correct, that's incorrect, that's good, that's bad. It will churn, it will not churn. So all these labels were provided to the computer. So this is called supervised learning. Unsupervised learning is model tries to identify patterns in unlabeled data. Example, clustering, dimensionality reduction, and all these things. So unsupervised learning is a type of thing that you are just providing a data set to a computer, and you say, okay, learn it by yourself. Identify me some patterns. What do you think? See, so computer will learn that. The computer doesn't have any pre-labeled data there. Computer doesn't know will the customer churn or not churn. You see, in that regression model that we had a column that it was 0 and 1, if you remember. It was showing that the customer churn, not churn. Yeah. So that was a label data. But if you just provide us a solid data set to the computer without that column, without that specific column, and you see that these are the whole the situation of customers. They bought in this time period, This was their was last purchase. This was their first purchase. And this was the time since. So this is the data set. Now, learn the patterns from this data set and give me the and decide based on these clusters that um, based on this data set, decide the clusters. Which cluster of customers will be under churn? Which cluster of customers will be under not churned? So this is how the unsupervised learning works. It means that actually you don't know the pattern yourself. You're just asking the computer to understand the pattern, if there is a pattern existing. In reinforcement learning is the model learns through trial and error by interacting with an environment and receiving rewards or penalties. So this is another type of learning. It's called reinforcement learning. So model predicts something, then it assesses its performance. You know how to some of the performance evaluation scores. Yeah, we already explained that to you previously when we were studying regression models, how to evaluate the model's performance. Yeah? Through positives, through negatives. So these sensitivity analysis, accuracy scores, there are different types of other types of scores that you have to evaluate the model's performance. So when the model predicts and then evaluate its performance, then from that performance again the model starts fine-tuning its parameters and conduct the training and in predicting again. Then from that result again model understands. So this is how the model evolves and how the model learns from the within the environment when it's having an interacting environment. These chatbots, which are working with you, you're giving your whole data to them, ChatGPT, Gemini, or other things. This is a type of reinforcement learning because they're learning from you as well. So they're getting your data and then retrain themselves again and refine their responses specific to you again. But they are very large language models, and large language models are programmed in a different way. They are programmed that a specific cluster will be improved, not the whole LLM. So because your data is very smaller to the whole data that the LLM has. But still, your data is there, and it gives the improvement to the LLM again, and you're improving the LLM actually by putting in each query to that specific LLM, and LLM learns that from you and puts it back to their machines. This is how these LLMs or these companies, they are making money out of you. Um, I wrote an article a long time ago that actually data is the future currency. So no money will be important future. Maybe not that long future that you will not see that. You will for sure see that, and that's actually the currency uh, instead of the money that you're thinking. So that's the future currency is data, and this is how your data makes money. And but you don't know it. So this is what you don't know it. So this is how it works. Recommendation engines, they are calling it recommendation engines. Recommendation engines or another type of reinforcement learning. For example, if you open a YouTube video and there is an advertisement there, yeah, and okay, you have to watch it, for example, for 10 seconds or for 15 seconds, then you skip it, yeah. So actually, by watching that, and which it's enforced by you to you that you have to watch that, they're making money. But how the reinforce that's those ads are bringing to you by a recommendation engine. Recommended videos, for example, to you, recommended watch lists to you. Those are all called recommendation engines, which are based on reinforcement learning. Whatever you're clicking in your Not only, for example, if you're opening a YouTube, then there is something called right right now it calls cookies. Yeah. Previously, so whatever, you just no one reads all those terms and conditions. Yeah, you're just accepting, accepting, accepting. So whatever clicking you're doing, this recommendation engine understands. Okay, he clicked from 4 apps. He clicked on this app, so he's interested in this topic. So automatically reinforcement, this recommendation agent learns from your behavior. For example, sometimes it was then they said, okay, no one is clicking on these ads. We'll say that, okay, no one is clicking on these ads. Yeah. But what is how now the recommendation engine learns from you? Whenever you're watching an ad, and if 10 seconds passed, and you're just waiting that just to click the skip, okay, that's a skip. So nothing the recommendation engine learned from you. But if 10 seconds passed and you still want to just have a look at the ad, yeah. So you're doing nothing. You're not clicking anything. You just want to watch it till the end, yeah. Automatically, this screen time, which they're calling it right now, screen time. So these softwares, these applications, YouTube, Facebook, and whatever applications that you're using, they now have another point embedded in their engines that's called screen time. How much time, seconds, or minute you have watched something, an ad, or just a YouTube video or a video, so all these things. So screen time is also getting recorded. So it means by all those cookies that you're accepting, actually you're giving permission to all those softwares to analyze all those data. And that's called reinforcement learning by the recommendation engines. And next time, if you click on an ad, next time the same category from that ad will be coming on your screen. So, and they are making money out of it. And this is how the machine learning works. But this chart is a bit very much clear understanding of the machine learning, not only based on these three ones, but maybe uh, we will discuss semi-supervised as well. Now look at this. If the data is labeled, as I mentioned to you, so that's called supervised learning. In the supervised learning, we have continuous learning and we have discrete learning. You see, you remember we had continuous learning. That's called regression. If you remember that one. So we predicted from the fishes data set. If you remember, yeah, we have types of fishes. We have the length of fishes. We have the weight of fishes. Yeah, and we have labeled data. So which fish, which weight, which length, how much will be the weight of that fish. We give this data to computer. Computer uh, learned the pattern because the data was there, and that was a continuous regression. We are calling it linear regression. Yeah, we learned this one, and then we provided computer with another list of lengths of the fishes, and it gives us the predicted weight for those fishes. So this is called regression, linear regression. That different types of models, it load forecasting, power generation forecasting, and storage capacity forecasting. So different types of things that uh, uh, um, you are doing. So this is from a specific. I got this from a specific context, from an engineering context. And why I was just giving to you, just you can ignore the examples here, but you can just understand the concept of supervised, non-supervised learning. If that supervised label data we want to predict, and that's discrete. Discrete means we had classification. Yeah, we had yes, no, binary classification. Then we have to use logistic regression. Yeah, and there are different adaptive things or how. For example, naive Bayes is also one of the classifications. For example, that we can use. All of these are the names of the different models, kind and model. For it. Lots of models are there under classification. So, for example, in a power context, in a power engineering context, um, load classification. Yeah, so high load, low load, for example, and mid load, for example. If you want to decide about that, then you will be using that classification method. So because you will be having categories. Whenever you're predicting categories, that will be the classification. If you're predicting numbers, that will be continuous, that will be regression. But if data is not labeled, then that's called unsupervised. And within unsupervised, we have continuous and we have discrete. So for continuous, we have to have embedding and then autoencoders are there, PCA, correlation filters. So different types of things or the models are there, and you have to, for example, predict. Uh, uh, mm, you have to use the models which are based on embeddings. But if the data is discrete and you're predicting a discrete target, then you have to use clustering. And for the clustering, you have to use k-means, k-nearest neighbors, and similar models here. But if semi-supervised, which we said reinforcement learning, they are calling it semi-supervised sometimes because why the difference between reinforcement and semi-supervised? There's no difference between them. But the point is that for the semi-supervised, for the reinforcement as well, if there is an LLM, so they will learn it by themselves and do all the tasks by themselves. Yeah. So they will improve themselves again, uh, retrain themselves again, in just like type of an AI. It's a type of a robot. But in semi-supervised, which is a very practical model that we will be dealing with that type of modeling, there's actually a human intervention is required there. And why that human? What will do? Human will just start that retuning or parameter tuning process there. So that would be a human. When a human in the loop is required there, then they are calling it semi-supervised. It's not supervised, but semi-supervised. Um, Generative models, for example, if there is a model, generative model, yeah. So these AIs are all called generative models, self-supervised, and within the self-supervised, and reinforcement learning. For example, what I give to you the example of the ads, advertisement, recommendation engines. All these are reinforcement learning. Generative models are currently appeared recently. So previously, semi-supervised and reinforcement learning were the same category, but recent after 2021, 22. So now they added this new generative model that these AIs doing it by themselves. So they put it as a category, but still they're part of one thing. If human intervention is required for the model to reload, define, tune it itself, then that's called reinforcement learning or semi-supervised. If not required, actually, so the model learns from you. So these AI chatbots, they're learning from you. This is um, how it is. Now coming to the machine learning pipeline. So this is very important because you have to understand that the pipeline is important. Where to start, how to. So it starts with the data collection and data preparation. Data preparation is very much important in machine learning because if you feed um, look, why the revolution of ChatGPT happened? Why this company, a very small company, and not known company like OpenAI, just was in the position in 2021, 2020? I think really don't know when ChatGPT appeared. Why they were in the position to launch such a huge generative AI model, and why superpowers in the tech industry like Microsoft, like Google, they were not in the position to do that, while Google has the whole data of the whole world is in Google search engines. Yeah, so they have all the data there. Why they were not in the position to do that? The thing is that whenever the whole thing is in regard to it covers, it just comes under the data preparation. Google has the data, but the data was not prepared properly. That in order the computer should do the reinforcement by itself. A small company came and got access to that data and said, okay, I will prepare the data, reshape the data, and will fine tune it in a way that the computer will understand the patterns properly from it. So data preparation is very playing a key role, that you have to prepare the data if you want that your model will be predicting a proper result. Then data segregation, as I mentioned to you, training that split. You have to do the splitting of the data to training and tests, then training of the model, then model evaluation, and then after the model evaluation, model deployment, and model scoring, and then performance monitoring. So when the model is scored, deployed, then you have to do some model scoring as well. So this is called machine learning pipeline. So you have to understand the whole process and be expert in all these processes. Now coming to the data pre-processing and feature engineering. So this is preparation of the data and segregation of the data. This is called feature engineering and data pre-processing. Within the data pre-processing, the first item which comes in our mind, that's handling missing data, outliers and imbalances. So these are very playing a key role. What is, if you're dealing with a real world problem, then a real world data set, I'm sure 100% that there will be missing data. So how to handle the missing data? Either by imputation. Imputation of what? Mean, median, mode, or dropping rows, columns. So these are different things that you can do to impute the missing values. Till now, for example, we in our previous experiences, what we have done when we had some missing values, we just drop the value from the column. But you have to understand now, you're in the position to understand properly the mean, how to impute that missing value. Impute the missing value or replace the missing value with a mean of that sector, with a median, or with a mode. So these are the different things that you have to understand. And why now you understand these mean, mode, and median? Because you learn properly the distribution. You now understand what are the distributions of the data. If distributions are right skewed, left skewed. So if this right skewed, which mode, which of these measures you have to select? If it's left skewed, which measures you have to select? So this is now you have proper understanding of select which type of these things, these central tendencies to impute your missing data. Outliers. Outliers can be handled by capping values, removing outliers. You're using robust scalars. Robust scalars are one of the interesting topics in machine learning. This computer is actually doing that for you based on the scaling the data. It's a topic that we will be covering later on. You will see it then later on how robust scalars works within machine learning models. But lots of these models now they have put these robust scalars scaling the data. They have put it. They prepared libraries for that or functions for that. So type of built-in function within these machine learning models. But besides that, for outliers, you have to understand what is capping values. Capping values is the way that we have done previously. We said, okay, we defined the interquartile range of the data. We multiply that by 1.5. And we said, if it's larger than that or lower than that, so we will be dropping those values. That's called capping values. You have to prepare a cap, upper cap and lower cap for the data points. And beyond that, or beneath that, you have to remove those values. So this is called dealing with outliers. But also there is another type which you have to just remove the outliers. Simple thing, you're removing the outliers. But as I mentioned in one of my lectures previously, removing outliers is a very solid decision. You have to understand the impact of that as well. You have to understand if that point is actually incorrect data point, then you can remove it. But if it's a correct data point, removing that will impact the whole spread of the data. Now, imbalanced data. So this is something that you hear now. Techniques include oversampling minority classes. For example, smooth techniques, for example, undersampling majority classes, or using a class-weighted model. So what is imbalanced data? Just how to give you an example. Oh, just giving back to that example of customer churned or customer not churned. Yeah. In that example, if you're giving that model to the computer, that data set to the computer, and for example, you have 100 rows in a data set, yeah, and 7 of them or 9 of them, they have churned, which is 1, yeah, that the class was churned, yes, and 91 of them, they didn't churn, so it's the class is no or 0. This is called imbalanced data. You know why? Because the model learns, the model learns from you, from learns this pattern, but because the majority class is very high, the majority class, which is the 0, it's very high, it's 90%. Because of that, the score, the accuracy score of the model decreases. Model doesn't understand or doesn't learn properly the patterns between the yes, no, between the churn or not churn. Because lots of the data points are 0 or not churn, yeah? So lots of data points all belong to one category. This is why the computer is not in the position to learn properly the patterns. When this is called imbalanced data. Now, what to do with imbalanced data? There are different techniques. They are calling it undersampling majority class. So there is a technique that you are actually reducing the number of, for example, these not churn, for example, these 0 class or not churn class. So you're undersampling them and not feeding the whole of that class to the model, but a portion of it to the model, because you want to balance the data between yes and no, between both categories. This is called, for example, undersampling majority class or oversampling minority class. So you can do the same way, vice versa. There is only we have churned 9 or 7 or 10 of those data points. You can oversample that. You can generate synthetic data for those minority class and put it in the model in a way that the model should learn from that. So that's called oversampling the minority class or undersampling the majority class. So this is called the smooth system function in order to handle the imbalanced data. If you don't consider the balancing the data, then you will not be in the position, your model will not be in the position to accurately, properly predict something. And what is class weighted models? That's different things. You have 4 or 5 features, and then one feature has you have 4 or 5 features. One feature, for example, weight of the fishes that we wanted to predict. We have length of the fish, and we have height of the fish, and we have weight of the fish. Yeah. Now we wanted to predict the weight of the fish. Good. In order to predict the weight of the fish, we said, okay, we will be a linear regression model. We will be developing a multilinear regression model because we have two of these numbers. Yeah. Now, previously we had only one of them. Yeah, height or length of that. Now we have weight of the fish as well, if you remember that one. Now, coming to that, okay, we did the prediction. The prediction result is actually something 60%, which is not satisfying. Why? Maybe weight of the fish is not playing that much role in the weight of the fishes. This is called class weighted models. It means whenever next time I am developing such a model, I'll put a weight of, for example, 70% for height and 30% for width. Both of them are explanatory values, both of them are features, both of them are very important features you have to consider whenever you're developing the model. But you're saying the model that, okay, from both of these features, based on these patterns that you want to discover and predict the weight of the fishes, I want you that you should focus 70% on one feature and 30% on another feature. So this is how different things work. So just is it's a very simple example of how you impute the missing value. See, this is feature one. This is feature one, feature two, and target. So we have, for example, I just mentioned to you, assume that this is height of fish and this is width of fish, yeah, and this is target is the mass of weight of the fish, yeah. And here we have now, see, this is if this is missing value, so this prediction is actually wrong. This target prediction that we have done, that would be wrong because there is no value and no relationship will be discovered by no pattern will be discovered by the model. You have to impute it by something. You have to impute here. We did 𝗟𝘃𝘃 using 𝗟𝘃 feature one by using the mean of this. The mean is 2.4. We added 2.85. So we just added 2.85 here. See, this is 2.85. This is the mean of this value. We imputed that. Now, this is how you have to impute the missing values. Now, coming to the one more thing. This was so this is type of data pre-processing and feature engineering. So first thing you have to do, handling missing values, data and outliers and imbalancing. Now, second thing is you have to feature scaling and encoding. So what's feature scaling? Ensures all features have a similar range, improving model stability. So if common methods, standardization, z-score, or min-max scaling. So what is feature scaling? If your features, for example, you have a feature, what is similar range? Similar ranges, how to measure the range? What is actually come to your mind whenever we are talking about the range? What we want to measure? Who can tell me?
I think it means that, for example, if we want to use the weight as a feature one, the weight should include from minimum to maximum value. It means the data set should contain max value and min value in the same glance.
Not just in regard to the range, if it comes to someone else's mind.
Sir, I would say it's more of like or measuring the range of how variables relate. For example, with feature scaling, it could be independent variables, or in a way, the features of the data that we are seeing.
Yeah, good. So, yeah, that's good. But simple question was that, for example, here it says ensure all features have a similar range. How do you think that it would happen?
Does it mean that there shouldn't be any outliers within the data, sir? I'm not sure. Sorry.
That's okay. This is just that we want to remember that the previous things that we use to understand the range of the data. So range of the data is actually is, if you remember, Q3 minus Q1. Yeah, if you remember that one, we said that we
Yes,
have four 4 quartiles. Yeah, we have Q1, Q2, Q3, Q4. And the range of the data was Q3 minus Q1. That was the range of the data. If you see, look, if you see that we want to have a similar range for all features, that's not possible. You know, that's not possible. Why? Because different data sets, different features have different values. How you can want, for example, if a feature is about the height of something and another feature is a bit about the width of something, but how you want to make them similar? We don't want to make them similar because there are different numbers and figures out there, but we want to actually, at least, we want to make the range of those the data values of those columns similar. It means that at least the Q3 minus Q1 of that one feature at least should be similar to the Q3 minus Q1 of the another feature as well. Why that's important? It means that you have to deal with the outliers. We have to remove the whatever you said right now. Both of you, you're correct. But this was the concept, one step behind it. And dealing with outliers, because whenever you're removing outliers, you're scaling the data. So that's actually scaling. You're scaling the data, and this is called scale of the data. And this is very um, uh, important. And there are two ways of doing that. One is called standardization, which is called Z-score, and another is called min-max scaling. Min-max scaling. So this is the what I say to you. So the minimum, maximum value, that's called a scale. And another thing is encoding the categorical variables. This is very important. If you remember, we have churned data set. Yeah, we have a data set of churned or not churned. Yeah, and there was just yes, no, or churned, not churned. There was categories, and there were texts there. So computer doesn't understand the text. If you put those categories there, yeah, maybe developed models, they're now dealing with those things, but still, all the time you have to understand the encoding. Sometimes there is no need to have texts within your data set. Encoding is not only for the target variable, but also for the explanatory variables. You can have encodings. If there is response, for example, or if you have countries, only 4 countries, for example, in your data set. A column, there's a column, you want to analyze a sales forecasting, yeah? And there is a country column. In that country column has values. For example, just name of 3 countries or 4 countries, maximum 5 countries. Whenever you're dealing with that with a modeling, you have to understand which categorical values you can encode them. So with yourself, within your understanding, you downwrite it for yourself that okay, I will put for country A, I will put 1. For country B, I will put 2. So instead of texts and name of the countries, you're putting 1, 2, 3, 4 there. So that's called encoding, label encoding, one-hot encoding. These are techniques that you have to use for the encoding of categorical variables. So if you have list categories, 4 categories, 5 categories, all the time try to encode them into numbers. That way, if you have a very large data set, that way actually you're developing a model or you will be developing a model which will be very much accurate in understanding all the aspects and everything. For example, we have categories A, B, C, D. Look at these categories. And we have feature 1, feature 2, and category C. These are categories, yeah? So one of the one-hot encoding is actually you're doing the category encoding. So the category A, category B, and category C, that will be encoded automatically. Look at this. This category A, category B, category C, which are there actually, they are getting encoded automatically. This is it's called one-hot encoding. It's already from sklearn library. You can download that. That's called encoding, one-hot encoding. As I mentioned to you, you can do it by yourself, label encoding. You can do that. I can say, okay, category 1 will be 1, B will be 2, C will be 3, yeah? But one-hot encoding did something else. One-hot encoding is actually defining the relationship between these features as well. Feature 1, feature 2, feature 3. So it defines the relationship between the feature and between the categories and define a value there. So for one of the categories, it said, okay, it should be 1, for another -1, 1 -1. So it just defined two values there. For category B, it did the same way. It put some value here. So these are called encoding. So it changed the category values based on those features into the numbers, which is very much important whenever you're developing the models. Now, scalar, standard scalar. So for these features that we had, for example, they put the encoded back to the X scaled. They're called it X encoded and X scaled. They're calling it. They put it again and scale the data. So now, if you see the range of this data and see the range of this data, so these features, they will have similar ranges. So both of these columns will be having similar ranges that we said that we should ensure that features have a similar range. So this is how the feature scaling in encoding works. I hope you understood this, what is actually how the feature scaling and feature encoding works. Now let's come to another topic, which is also out of this, in continuation of this. For example, we will be talking about the feature selection in dimensionality reduction. So this is one of the another type of very important topics here. So we thought it's also under the data pre-processing and feature engineering. First of all, you have to deal with the outliers, you have to deal with the missing values, you have to deal with the imbalances. Another thing you have to consider, that's feature scaling and encoding. And another thing which you did feature scaling and encoding, but dimensionality reduction in feature scaling, that's very important, playing a key role. And what is that actually? So these are very important topics for the feature selection. You may have different types of features, and you may have different types of columns, but one of the main things that you have to understand, which column you have to select. For example, you have a table with 30 columns, and only one column is the target you want to predict. Assume a health data set, yeah, a data set from a laboratory, yeah, and you know how many components are there in a blood test, yeah, at least 20. If you see, I hope everyone will be always healthy. But if someone gets those lab results, there are lots of features there, yeah, indications. If you put all of them a data set, and then, for example, you want to predict the possibility of a disease, you want to create such a model to predict a disease based on the blood tests. Now you have to understand, actually, all of those features are important, relevant. You want to keep all of them. Is it required to keep all of them or not? So that's an important question that all the time you have to ask, and before doing any model development, you have to think about it, that either is it possible, is it required to keep all those features or not. Another thing, for example, choose features most relevant to the target using statistical tests, feature importance from models. Now, you know, we correlation matrix. Do you remember that we have developed a correlation matrix or a heat map, they are calling it. Why that's important actually? It is important because it gives you the relationship. I hope you remember that before regression we studied the correlation, yeah? And we said that there is correlation, then after correlation, we defined also the differences between correlation and regression. Now, you have to understand the correlation between each feature and between the time before selection of that feature for the modeling. If there is a positive or even negative, but there is at least a correlation exists, either positive or negative, not important which side, you can keep that feature. But there is, if zero, there is no correlation exists, why you want to keep that feature actually? That's not important then. So let it be the way that it should be. There is no need then to keep that. So this is called the feature selection. One more thing, which is called PCA, dimensionality reduction method in the machine learning. That's very important. What is the dimensionality uh, uh, reduction method means? It means that you are intentionally trying to not select a specific feature. While still you want to keep the structure of the data set. It is called principal component analysis. It's type of a dimensionality reduction technique, which transforms high dimensional data into lower dimensional form, while also it preserves as much variability as possible, or as much structure of the data as much possible. For example, you have a 3D data visualization, and you want to make it to the a 2D data visualization. So this is in regard to the dimensionality reduction. So these are the important things that you have to understand. For example, in regard to the 3D dimension into 2D dimension, because whenever you're analyzing pictures, analyzing videos, for example, analyzing, for example, uh, uh, computer vision, all of them are actually um, 3D visions, as you know, point with 3D dimensions. But how to understand when to convert that 3D into 2D? That's very important, and that's very playing a key role, for example. For this, I will just, I had a resource on PCs, a very uh, complete resource. I will try to, if it gets launched here. This is called principal component analysis. This is a topic that you can understand. You can so you can play with it. What we mean actually, yeah. So, oh, these 3Ds are not running here, so that's the problem. Here is a video here. So there's a video. I wanted to show you this video, but it's not running in this data set. But still, these are the points. You see, these are the 3D points here. But this is a look from this way. Yeah? So you have XYZ here. This is the points with the 3D dimensions, and then the output is back to the 2D. So now we see only one dot here, one dot here, one dot here, one dot here, and this lines or like that. Unfortunately, this video is not loading in this. I will share this with you. Then you will try it yourself and have a look at the video. It's not a video; it's a animation. But you will understand how the dimensionality reduction works from the animation point of view. So, look at my computer. I think there's a problem with my computer. I cannot even open the chat there. Send you the video. Still okay. I think it's not working. This is the dimensionality reduction technique that you can use that, and you can see that. So how to reduce the dimensionality whenever there are several dimensionality existing. So Now coming to the next lesson, which is supervised learning, and we will be starting with the regression, and I think you understand now the regression, the whole topic of the regression, but we will go through that very without any too much explanations for that. But still, you have to understand that runtime disconnected. I think no, it's connected again. That's okay. This is another major topic. It's type of supervised learning. Within supervised learning, as I explained to you previously, that's a very simple thing. Um, um, it means that we are giving labeled data to the machine, and machine will decide upon that, and then understand the relationships, and then uh, um, finds the either it's before going to the supervised learning, we have to also understand that it's discrete learning or continuous learning. So if discrete, so that would be we will be dealing with discrete, and if it's continuous, we will be dealing with the continuous. And why it's important? Because we have linear regression, which fits a linear model to the data, and we have polynomial regression, which captures nonlinear relationships by adding polynomial terms as well. So previously we studied this is all for the continuous models. We have a linear regression and polynomial regression. If you remember, we had the relationships that we studied till now. All of them were type of direct lines, yeah. But if they are not direct lines and they are type of they have relationship, but their relationship is not a linear relationship. For example, their relationship is type of parable, for example, is a type of curve, for example. So that type of relationship, but still there is a relationship exists. That type of linear relationship exists, but that line is not a straight line, but other types of variation of lines. So that's also part of a linear regression, part of regression, and we are calling it not linear, but we are calling it polynomial regression. The same formulas, the same thing that we have done, the same things apply here. Nothing less what you have learned, but only some from stat models that we developed. For example, for linear regression, we were bringing OLS. We were using OLS for the logistic regression. We were using logit function, but those also for different things we were using different functions. So, but the concept still remains the same one. Now let's try this one if it works. I think we have already have the look. We developed these ones. See, this is our X encoded. This is the data set that we have developed, the X large. And Y is look at the X large and when Y is important. We have this data set. Yeah, this is the data set. It has categories and it has features, different features. Yeah. What is now the X large, all capital X? It is the list of the features in categorical values. And what is the Y? Y is the thing that we want to predict. So this is how, so we encoded our data set. These are all categories, category A, B, C, and these are the features, feature 1, feature 2. So this is our data set, yeah? We want to predict something for this. We have a target, DF target, which is Y. We have to predict Y from this data set. Assume, for example, these are different types of fishes that we had previously. Category A was one type of fish, category B was another type of fish, category C was another type of fish. And these were the features, height and width of those ones, yeah? If you want to develop a linear regression model with that, first of all, previously we imported only linear regression. This time we also import train test split as well. Why train test split is important? Because you have to, as I mentioned to you, you have to change the split the data set into training and test. So you have to put a portion of data set that the model should learn from it, and then you have to put another small portion of the data set for testing, that you have to test the model based on that. So this is how automatically this is your X1, this is your X, these categories, feature 1, feature 2 in category. Yeah? All these categories, category A, B, C, these are all the features. Good. Now you want to have it X train, X test, Y train, Y test. So you want to split the X into training set, into test set, the Y into X set, training set, and test set. You're putting all these things like this, then you're using train test split, which is this function of X scaled df. This is X scaled df. See, this is X scaled. We scaled the X1, X here. This is the X scaled one, which is the encoded columns are there from there. So this is, we want to give it to this. And Y test size will be 0.3 and random state. So the test in Y, and the test size will be 0.3. What does it mean 0.3? It means that 30% of the data, we will save it for testing, and 70% of the data will be used for the training. So this is how you have to differentiate between the test and training the data. I hope you got the whole concept of this testing and training, yeah, because it's very important. You have a data set, but you have to split the data set still in order to make computer intelligent to understand the patterns there. But you should not give the whole data to the computer, because if the computer learns the whole pattern from that specific data set, then you have to find another data, totally new data, that you should give it to the computer, the computer should predict for you. Okay, the computer did the prediction, but now how you will measure that that prediction is correct? You don't have any reference. Am I right? This is why training testing is important. Because within that specific data set that you have right now, you have to divide it. You know the results there, because the results of your data set is already there, yeah? But still, you want to keep 20% or 30% of the data for testing. Because when you test, you have to have a reference to compare that test with that reference, and then score your model. Score your model's
Excuse me,
performance.
can you reshare the screen, please? Because like some other students also like having some issues with the screen sharing quality. I'm also like I'm not able to see the screen very well. I checked my connection; it looks fine, but the screen quality is not so good.
I actually experienced the same thing, sir. So I'd also like to clarify that as well.
Do you see my screen?
Yes, sir.
Yeah, yes, it's better now. Thank you.
This is how you are splitting and training the data, and that's very important because you have to score your model. Otherwise, you cannot score your model. And there is another function also called whenever we have unsupervised models. You have to keep into consideration that as well. We will be coming to that later on. That's called leakage, model leakage. Model leakage means that model is actually learned from the training data set, but still the training data set shares the data with the testing data set. So it means the model is actually cheating whenever predicting the test results. but it should not cheat, because you need, otherwise you will be in the position to test the model's performance. So this is how testing is important. So we assume that 30% of the data will be for the test, 70% will be the training, and then random state, if we have, because we have a um, generating some data sets randomly. For the next time, whenever you are generating the same random, it will be new numbers. While we are now developing a model, so you cannot develop new numbers all the time. Yeah, it means you are changing your data set actually all the time. Then this is why all the time you're putting a random state of, for example, 42, or maybe whatever you want. And that specific random numbers will be generating all the time. Now we have a linear regression model. This is a linear regression model. Previously, we used stats model, yeah, to bring the linear regression through OLS. This time we are using sklearn. Sklearn is scikit-learn. It means it's a science toolkit. Learning toolkit is developed an open source model which covers all these modeling aspects, and all these functions are built in within those models. If you remember OLS models regression, we have to provide the functions there. Yeah, we have to put all those functions in order that the model should generate the result for us. But these functions, those formulas for all those functions, are now built in within scikit-learn toolkit. And then you will fit the model to the train and X train and Y train. Then let's print the coefficient of these linear regressions. So these are the coefficient, and this is the intercept. This is how simply you can develop a linear regression model after the balancing data and encoding the data. This was in regard to the models. Now coming toward another concept under this models under the supervised learning, that's called regularization techniques. So what is actually regularization techniques, and why it's important for the data set, for the modeling? Regularization is actually a type of another technique that we are using majorly for these modeling. It helps prevent overfitting by penalizing large coefficients. So what is actually so ridges L2 penalty? Lasso is another technique, which is L1 penalty, performs feature selection, and elastic net is combination of L1 and L2. So these are the different types of measures that you have to take in mind whenever you're developing the models in order to prevent the overfitting and underfitting of the data. Overfitting of the data or underfitting of the data is another topic in models. What is actually model does when it's overfit or underfit actually? Model actually learns the patterns that you give it from a data set. So model, we have a test data set, we have a trained data set. Model has been trained properly, understand all the features, understand all the patterns. Model predicted for us the training data set as well. So it got the prediction from the training side as well. And model do it very well at, for example, how to tell you, 60%, 70, 80%, for example, 90% accurate. The model is accurate. But whenever you are giving a unseen data to the model, unseen data means the new data you are giving to the model. Model's performance actually lowers to 40%. This is what does it mean? It means that the model is only learned the patterns for that specific data set. Out of that data set, if you're bringing new data, if you want to predict new features and predict new targets, model doesn't understand that relationship. So that's called the problem of model. Or model, for example, is very good sometimes in prediction of is not good at prediction of the data set that you have given it to it. For example, we developed a model, and that model is just predicting something. For example, the accuracy of the model is 60%. But when you putting unseen data to the model performance gets, for example, 80%, 90%. So this is called the type of understanding the models overfitting and underfitting. And in order to solve this problem, we have to use the regularization techniques. The regularization techniques are called lasso L1 and ridge L2 regressions, and they are essential in linear models to prevent overfitting. And when there are large coefficients, it penalizes coefficients. It means please mute yourself. And this penalty encourages the model to favor simpler, more generalized solution, not only to a specific coefficient. For example, in this model that we have developed, look at these coefficients: 1.2, minus 1.9, minus 2.5, 1.29, 1.7. So somehow these models are these coefficients are somehow there. So these are the coefficients. But if there is a coefficient of 5, then you have to penalize that coefficient. Otherwise, the model will be overfitting. You know why? Because it will be much more in having that specific coefficient. It will be that specific coefficient will be affecting that. So this is whenever you're developing linear regression models, you have to keep in mind penalizing the coefficients. So this is done automatically by the model, by the models, and you can do that. For example, the ridge regression, which is L2 regularization, it adds a penalty equal to the square of the magnitude of coefficients to the loss function. So this is different types of understanding of that, for example. Typically does not set them exactly to 0, but retaining all variables in the model. And lasso regression is actually introduces a penalty equal to the absolute value of the magnitude of coefficients. So it's actually shrink some coefficients exactly to 0. Please mute yourself. So I will be giving you another source here. I think if it works again, I hope that will work. It's a type of scikit-learn.org. So from this, you can learn all the coefficients. Look at as a function of the L2 regularization. Yeah? So what are rich? So this is the whole theory is defined here. So the whole thing is defined here, and this is actually even the plots plotting that coefficients. And then this is the interpretation of the plot, how to interpret the plot and understand. Lots of other regularization techniques are here, and you can learn from here. So this is the L1, and this ridge was L2 regularization path. So this is the L1, for example, for the logistic regression path that we are having here. So different how to regularize it. However, these are the techniques that you have to you have to use whenever you're developing models. Now you will be coming to the evaluation metrics for the models. So those models, I think you understand some of these evaluation metrics. We will not go through that, but this regularization was new because we just stay a bit more on that. But for the others, there is no need because I think you know all those models if you remember them back. So mean squared error and root mean square error and mean absolute error R square. So these are all. Do you remember, for example, residuals in loss functions? I hope you remember that. Yeah. So those are the different things, for example, that we learned when we were developing the our linear regression model. So these are mean squared error, for example. What's mean squared error? All these errors, different types of errors, is relevant to the residual. If you remember in the linear regression, there is called a loss function. What's loss function actually? We had a line there, yeah, if you remember, and we had points, and then we had predicted points around the line. Look, this was one of the things. For example, this is the predicted dots, and these are the actual dots. So the distance between these two ones, these are very important whenever we are talking about the linear regression. And these are called residuals. And then different things, different measures have been developed based on only this distance. Distance between what? Between the predicted dot and between the actual dot. In all these things that currently you're seeing here, these names are all of them are based on these things. So this is mean squared error. So all these errors, some of them, so they took them average of them, then square that. That's called MSE. Root mean squared error. So they just from that squared root they took the from that squared error they took the root of it. So mean absolute error. So from that error, so they just took the average of that, and then for each data point, they took only the absolute value for that. And R square is actually the residual square for each data point. Then they took it. In this. So these are all the different aspects of understanding the of this regression models, and these are the values that you have to all the time measure whenever you are developing them. The same thing with the logistic regression we have done previously. But you have to understand that these are all built-in functions now within the scikit-learn library. Whenever you're calling those, you have to just understand them, how to use them, how to find them within the library, and how to call them. So those will be automatically bring to you back, and you will understand and analyze the results there. So I hope it's understandable to this point. So from this point later on, we will be doing the still to the supervised learning, and within the supervised learning, we will be now going to the for the classification problem. So we already make a classification problem, but which was logistic regression. But besides logistic regression, there are other types of classifications as well. So that's called, for example, you understand the logistic regression, but there are called other things as well, for example, that you have to learn. That's called decision trees in random forests. You will be learning what is actually decision tree and what's actually random forest in very simple words before going into the very details on how they will do that and how they are there. Actually, logistic regression is it predicts probabilities of classes using the logistic function. That's it, probability of class. If you remember, we had two classes there, yeah? So we detected two classes in this logistic regression. This was logistic regression. Class 1, class 0. We predicted two classes, but we predicted the probabilities of those classes. You remember? These are the probabilities. These are all the probabilities. It's called likelihood, if you remember. In order to, these are all the probabilities. These are all the probabilities with the likelihood. But in order to fit them in those classes, you have to just, we did a round off, if you remember. We did a round off, and then based on the round off, it become either 0, either 1. So this much become 1, this much becomes 0. This is called actually that within the logistic regression, you're predicting that this data is probably how much percentage close to that specific data set or to the category. So this is how you will be understanding that. This was the logistic regression. Decision trees was actually splits data based on feature values to create branches. What is actually decision tree? And you know you used already decision tree, and that you understand how the decision tree, for example, works. Use it. Do you remember graphing within a simple graph, organization structure, for example? So if you remember that type of a decision of a structure, so that's actually for this model you're doing actually the same thing. You are assessing the relationship between the features and between the targets, and then deciding, okay, which feature is affecting the target at which level. So different types of features affecting different types of target, and then you're doing branches of it. So several branches at the end. Then at the end, you will be having lots of coefficients, and then you're taking the one which is having the highest possibility. And then you're saying, okay, this category is actually is belonging to this decision tree. Random forest actually is instead of decision trees improve generalizations. So random forest is actually also a type of decision tree, but they're just putting it in a way that to show the decision tree, to generalize the decision tree, and making several trees together. So bringing several decision trees together, and this is called, they are calling it forests right now. So random forests. So this is how the for the categorical for the classification modeling, we will be using one of these things. Either we will be using logistic regression, I will be if there is binary solution. binary solution means all the time, if I'm saying binary, you have to understand that it's either 1 or 0. Yes, no. So a logical selection between yes, no. But if we have multiple categories as well, that's that's also possible. We can use logistic regression for that. We already learned that we can have multiple logistic regressions as well. But if we have more than two, hopefully everyone will go toward the decision trees, because decision trees are the ways that they can actually decide uh, upon the different things of something. I'll just give you an example. A very simple example. I hope my computer will work, and I think it never worked properly, but this time, for the decision tree, if you just see this very simple. This is a decision tree for awarding a loan to someone or not in the bank. It says, look how the decision tree model works. It goes feature by feature. So the first feature for this model was the age. Age is over 30, less than 30. So this was a KPI for the model. You have to define the first feature. The first feature was the age. Age over 30? Yes. Okay. If it's yes, let's go this side. Number of children. How many? For example, less than 2 or more than 2. You see? So this is another feature. So age was the first feature. Second feature for the same root was the children. If less than 2, yes, less than 2. So then get the loan. Give it the loan. Give the guy. So at least this is a very first rough assessment how to get a loan or not get a loan. So that's from a bank point of view. If number of children more than 2, less than 2, which is no, it means more than 2, then go get a loan. So you know why? Because there are lots of liabilities of the children, and age is also over 30. So it means the employmentability is also getting lower and lower, and children are also high in the numbers. So if you give them the loan, so how they will pay back to you, because they have other responsibilities as well. But this is a simple, a very realistic and a very practical way of how you have to understand how the decision tree works. Oh, if age is not over 3, less than 30. So if age is not over 30, it's less than 30. And the salary is over $25,000. Okay? At $2,500. Salary is over $2,500 per month. If it is, which is yes, so they will get the loan. If it is not, don't get the loan. So 2,500 is actually, I think, the minimum wage in the US. I really don't know, but this is how a minimum salary threshold was mentioned there. That if this is this much amount of salary per month, then if the salary is more than this, it means they are earning good. Then they will be paying back the loan to you. And their age is less than 30. It means they have full energy, working capability, employmentability is also there. So they will get the loan back to the bank. Otherwise, it will not work. So this is how a decision tree model works. A very simple understanding of decision tree. In decision tree, this is now you have to understand other things about the decision tree. About the leaf and forest and all those things, how the decision tree models work. Look at this. So the main one, this is called root node. This is called node. All these ones, these are called branches. See, this was the root node, and this is the branch. Yeah, so these branches, they have decision nodes. These are the decision nodes, yeah? This was the root node. This was the decision node. Each decision node had another branch, yeah? Yes, no. So the final one, this one, 𝗔𝗱𝘃𝘃𝗃, that's called leaf node. See, within this branch, there is no further branch. The final branch is leaf node. But if there is still a possibility to get another decision or branching it again, that's called decision branch. But if it reaches to the final one, then that's called the leaf node. So this one is the leaf node, this one is the leaf node, this is the leaf node, this is the leaf node. So these yellow ones are the ones with the final ones. It means it will not go further. The similar thing for the project management, you can do the same thing, and lots of things are there. So root node is actually the topmost node representing the initial decision. See, this is the initial decision that it represents to you. Decision nodes are actually intermediate nodes. It splits further into the branches and provides more conditions or attributes. Leaf nodes, they are calling it also terminal nodes. This is the end point of the tree. In branches are all those lines. Those lines have weightings as well sometimes. Then you will understand what is branching. So you will be coming to that later on. So this is how you will be understanding that. I will just put this code. I will see if this code runs here based on the this is type of decision tree. Yeah? So we imported decision tree classifier, and from that classifier we put from this for that data set that okay, we have such a data set, we have categories, we have features, and we want to predict category Y. And then if we apply that, so the decision tree accuracy, we want to just to define the accuracy of decision tree. It says 0.5 for the specific decision that has been taken above. But these are one of the things that for the supervised learning we are using. So the supervised learning for the classification we use, for example, first was the logistic regression, decision trees, and random forests. So this is one of the things. Another thing which is mainly used in you have to understand that's called support vector machines. This is also one of the interesting topics, and it's also for the classification problems. Whenever you have lots of classes and you want to classify or categorize find the relevant categories, then you will using the support vector machines, SVMs. SVMs finds the optimal hyperplane that separates classes with maximum margin. So it actually, what is the SVM does? SVM does finding a very fine-tuned boundary between the classes. So when that fine-tuned boundary is found, then with the classes with a maximum margin. So whenever that margin is found, or that which separates the classes, the optimal one, the classes, then you can very easily define the different classes and different categories. So this is how the SVM works actually. It's actually not very standard understanding of the classes specific, but it's actually the defining the boundaries, the optimal boundaries between the classes. you have 4 categories you want to predict, or you have 5 categories you want to predict for those categories, or you have 10 categories you want to predict for those categories, specific a target for the specific 5 or 10 categories. So SVM is actually is actually finding the specific those maximum margins and optimal boundaries between those categories. It's one of the good use of machine learning models, but it's not usually used by all of these data scientists with small data sets. It's usually worked with large data sets, and its calculation is also not that much difficult with the scikit-learn function that we are having right now. It's very easy. So this is how the different classification models that we have to understand. Now we are coming to the evaluation matrix for the classification models. So we have supervised learning, and we had the classifications in not and discrete and continuous numbers. For the continuous, we use regressions, linear regressions, and for the classifications, we said, okay, we can use logistic regression, we can use, for example, um, decision trees, which are very much important, and also we can use, for example, random forest, which is a combination of decision trees. Support vector machines is also another type of this algorithm. It's also used for these classifications. This is why we mentioned it there. And actually, what is the concept? We have three things in this SVM. One, we have hyperplane, which is there. Another is margin, and another is support vectors. So these are also things that you have to understand. For example, data, in which data, I will just give you a very solid, I'm trying to find a very solid understanding of support vector machine. So now all the time I'm trying to find you proper visualizations in photos to give you a proper understanding of what's going on there. Because these are very complex topics whenever you're looking at it theoretically from a wording point of view. But it's very easy whenever you're looking at. So this is hyperplane. This is the whole space of this feature, and this is feature space axis 1, and this is feature space axis 2, and we have two classes. We have class A and we have class B. SVM actually is doing what? SVM is actually doing to find this boundary between two classes. You got the concept now properly? What this very difficult topic means? So what is margin? Margin is actually the distance between the hyperplane and the nearest data point. So this hyperplane is a dimensional space, as hyperplane is a flat subspace of dimension, divided space into two half spaces. So this is the hyperplane. This line is hyperplane.
Sir, is it similar to the regression line?
It's not regression line.
No, like similar to that.
It's not similar to that. Regression line is not for the classification. Regression line is for the continuous numbering. See, this is the regression line. For the regression line, there is correlation existence. This is the space. This is regression line. All the dots are around the one line. This is not for regression line. This is classification. It does classification between two classes. For example, this type is class A, class B, this point is class A. This is called hyperplane. These distances are called margins. This is SVM, simple thing. This is SVM. This is used specifically for the uh, uh, classification purposes. It can be this type. It can be different lines. So different types of things that margins are there, separating hyperpalates or support vectors. This is another very solid understanding of these hyper. It can be it might be having separate two classes, three classes, whatever classes. Then it depends on how many hyperplanes you will be having. So this is called separating hyperplane. These are support vectors. These dotted lines. See, these dotted lines are H1 and H2 are support vectors. Margin is D1 and D2 is the margin. It means the distance between the hyperplane and between the support vector is the margin. So you see, these are the things. This is how SVM works. It's a very simple model visually. Now we will be coming to some evaluation matrix, but these evaluation matrix we will be not discussing more, because you already having a very proper understanding of this evaluation matrix. We're just putting it in this notebook for you, but we will not be discussing it, because one of the very toughest things that you have, for example, confusion matrix. You understand what's the confusion matrix, recall, if one score, precision, accuracy. These are all the evaluation matrix for these models, and you can bring it from different points, understanding it from different point of view. And if you remember the confusion matrix was the true positives, true negatives, and all those values that we learned, if you remember, for the logistic regression. So how many observations were true, how many observations were false, and how many the model predicted for the truths predicted false, and how many for the false predicted truths. So those were the terms that we used this different metrics. Also, that's called. We understand that what's the accuracy of the model. I think we learned it here, and okay, without showing that, this was the accuracy. See, and this is the proportion of correct predictions. Accuracy is the proportion of correct predictions. True negatives plus true false divided by sum of all these ones. That's called the accuracy of the model that we have developed previously. So for the remaining thing, for the precisions and recall, and if one score, it's also based on confusion matrix. Whatever the main thing within these two evaluation metrics are the accuracy and the confusion matrix. If you understand the confusion matrix, then from the confusion matrix, you can decide the precision, you can decide the recall, you can decide the F1 score, and all these things. This is just a play around of the confusion matrix and understanding the true classes which has been predicted. For each thing, they just put it a separate name for that and made it very complicated, but that's not that much complicated. It's the simple and easiest way that you can do that. Our next topic actually will be the unsupervised learning, which is so supervised learning was to this point. We will be now going to the unsupervised learning, and we will be starting from within the unsupervised learning, we will be starting with the means clustering and with hierarchical clustering. So those are the two things that we have to proceed with, and we have to understand it. But still, I think we will be learning this tomorrow. So as I mentioned about the evaluation matrix. So okay, assume that we have developed a model which is predicting a very simple thing. You're providing the model a picture, then model decides is it an animal or not animal. You got the concept of the model. So this is now the model that we have developed, and this is the confusion matrix. It's a very simple confusion matrix. Is true, yeah. So it's false, and this is false, and this is true. So these are the actuals, and these are the predicted ones. So these are the actual ones, and these are the predicted ones. So how many from how many pictures we have provided? 1, 2, 3, 4, 5, 6. For the 6 pictures that we have provided, this model predicted actually. So 3 of them, it predicted that it is actually the animal. Another thing, 1 of them, it predicted that it's animal, but actually it was not animal. See, it predicted this one also as an animal, but it is not an animal. It predicted 2 that not animal, and actually they were not animal. So now all these precision scores, they call if one score, everything is about the confusion matrix. So how many true positives we have? 2.
2 positives.
True negatives we have 3. Yeah.
Yeah.
False positive we have 0. False negatives we have 1. What is accuracy? Accuracy is actually the true positive plus true negative divided by sum of true positive, true negative, false negative, false positive. Yeah. So this is the accuracy of the model. Do you remember that one? Then that's 83%. It means 83% the model is accurate. What is precision? Precision is actually the true negative divided by true negative plus false negative. How many true negatives we have? We have 3 divided by true negative plus 1 false negative. So precision is actually 75%. What is recall? Recall is true positive, true negatives divided by true negatives plus false positives. See, we have 3 true negatives divided by true negatives plus false positives. We have 0 false positives. Then recall is 100%. If one score is 2 by precision divided by precision multiplied by 1 divided by precision plus 1. 86%. This is F1 score. So you see, all these measures are actually a different way of combining and playing with the confusion matrix. The only main thing that you have to remember and memorize, that's actually the confusion matrix. That's it. So that is the main thing about the understanding of confusion matrix. Tomorrow, hopefully, we will be learning the unsupervised learning, and I will just put it here. I don't want to forget it for tomorrow. And unsupervised learning, this will be a major topic. And within that unsupervised learning, we will be starting from the clustering. So first of all, we have to understand the clustering. But in the clustering, we will be starting with comings. So I think that will be the most important thing. And that's it for today. If any questions, please ask me.
Thank you so much for your hard work, sir. We really appreciate it. I just wanted to ask if it's possible to get a copy of the Foundation of Statistics notebook so that we can review it, because personally I'm having a bit of a hard time grasping the ML topic, and would really appreciate being able to recall the Foundation and Statistics as we move forward.
So I will try to find my today or tomorrow the time, and I will be just uh, completing that and uploading the whole statistics module as well.
Thank you so much, sir. Really
Yeah.
appreciate it.
Yeah, thank you. Any questions, please? So it means everyone is now understanding the topic, and that's good. That Yeah, thank you, Ashley. Good. I really don't know how many of you has completed the Kaggle certificate. It's a long time. I didn't check that one. I get notifications, but I wanted to understand how many of you has been completed. 30 of you. That's good. That's good. Only 13. That's good. Okay, our session is officially completed. Then any questions? أنا سأول باي بوشم مش هسأول كنين.